intermediate polar plot construction method, how to get the polar plot, okay, and what is the method, what is the approach we should have to know, and polar plot example. Now, what is the basics of the polar plotting? Very simple, and the plotting is here, okay. Understanding the basics. So, what is the basics here? The polar plot, polar, polar means what? Okay. So, you must have to know what is basically polar. Polar means basically the polar form of any phasor. So what is a polar form? You can say, suppose you have the the phasor having representation, a vector having representation A plus JB, where it is the real part and this one is the imaginary. So what we are getting the representation of any phasor quantity. So polar, this is basically the representation of the phasor that is in rectangular representation, where we are going through the polar representation that will be in terms of magnitude and phase, right? So they are having a particular magnitude, they are having the particular phase, as because it is a phasor or vector having its magnitude as well as direction. So magnitude as well as its direction. So this form is called polar. So that's why whenever the vector or the phasor that is representing with respect to certain parameter, and what is the form? Magnitude and phase along with, magnitude and phase along with, that will be termed as a polar plot. Let's see what is the definition of set. Polar plot is a plot which can be drawn magnitude and phase of a phasor with respect to the variation of the angular frequency in its domain, right? So what we are trying to represent, we are trying to represent the magnitude along with the phase. Magnitude along with the phase with the variation of angular frequency omega. What is the range of omega we have chosen for the polar plot? That is the whole range 0 to positive range. That is positive range of omega that we are considering 0 to infinite. So for the polar plot, what we will find? We will find that for any phasor quantity, or you can say the Hausdorff function mainly for the control system, that will be represented in terms of in phi form. That is nothing but the polar form of that phasor, right? And that what is the variation of the magnitude and along with the phase with respect to omega, with the whole range 0 to infinite positive range, that will be depicted in the graphical through the graphical approach. Okay. Now that is the main objective or theme. Okay. So what are the steps? What are basically main concern here? The magnitude are represented by the normal values only, and the range of omega is positive. That is whole range of omega in the positive part, that is 0 to infinite. Okay. Now how to do it? So what is the explanation I have suggested over there? That is we will be starting with the qualitative, because any system will be represented with the open loop transfer function only. Okay. So for sometimes HS may be divided as unity most of the time. So we will be handling only GS. Okay. So will be sometimes it is represented by only GS also. Now, as it is the frequency domain, frequency response analysis is also a frequency response analysis. While we will be going through that flow of this basics, so what we will find that it is nothing but a frequency response analysis. As because see, what is the range of the independent function we have suggested over there? That is omega, angular frequency. So obviously it is representing frequency response, right? It is representing frequency response analysis. Okay, so that's why whatever be the weight that is GSHS, we are putting S equals to J omega. That is steady state response we are considering as because it is frequency response. That is our concept from the previous class we got. Okay, so the polar form of GJ omega we have to find, and that is the magnitude. Obviously, as it is a phasor, so having its magnitude as well as phase. So rectangular representation A plus JB, that will be transformed into the representation of polar form, magnitude, phase. Okay. So, and both are depending on omega, and what is the range of omega we have suggested? 0 to infinite for the polar plot. Okay, for different kinds of plotting, gradually we will be coming through in my next lectures. Okay, so there are the different kinds of plot available. in the frequency response analysis. But in case of polar plotting, here the range of omega that is suggested from 0 to infinite only positive quantity, and here the WLTF that will be considered as basically your WLTF that will be considered as basically here GSHS, and where it is the function of omega, magnitude as well as phase of GSHS, and that omega will be ranging from 0 to infinite. Okay. Now what is GG omega? That will be in M phi form that I have already given that concept. Now M is depending on omega as well as phi is depending on omega. That's why it is frequency response. We are analyzing frequency response. And what is the observation? Observation is that omega will be varied from 0 to infinite. So both the magnitude and the phase are the functions of frequency. That is the note. Okay, keynote is magnitude and phase both are function of frequency. So that's why it is frequency response analysis. Okay, and omega will be ranging from 0 to infinite. It's very important. It's very important. Okay, so what we will get? We will get M phi. Okay, the locus of tip of the phasor, that is nothing but M phi. Okay, with the frequency omega is called polar plot. So it is very simple. You have any phasor given. That phasor may be a system representation. Okay, that system representation is basically GSHS. And if we are telling that it is not a system representation, it is a response representation, in that case, we are talking about the impulse response. While we are fitting the input as what I am telling, let's see, system response. If we are telling that this is frequency response is system response, then what we are telling that this is the GSHS LTF of the system GS, right? And we are getting here suppose CS as output and RS as input. So in that case, if we are handling only the WLTF, that is representing basically what I am telling, impulse response. We are going towards impulse response. Okay, impulse response. Why? Because RS we set to unity. That means it is nothing but the impulse response. Okay, RS is unity because delta function, direct function having the Laplace transformation, we are getting unity. So if we fit that input inside the system with the RS equals to unity, so what we are getting, GS equals to HS, GS equals to CS. So output or the response of the system is directly equals to GS. So that's why we are dealing with the unit impulse as the input and output is CS, and that is equals to basically GS. So we will handle only GS in that case. Okay, and GS is nothing but the function of phase. So obviously it is a phasor. So phasor having its rectangular representation as well as the you can say the polar representation. So in case of polar plot, that polar representation, polar means the phasor having magnitude and along with the phase with respect to frequency that will change, and that locus of the tip of the phasor with respect to the frequency is called the polar plot. Okay, it's very simple to analyze. So polar means polar form of which the system or the signal, you can say the output or the response. If the system is exciting with a unit impulse, always it is suggested that, so we will be our analysis will be with the WLTF. Okay, that is basically for the simplification purpose. We are taking RS equals to unity and GS will become CS. So it may be represented as a system system representation, characterization, or the you can say the output or the response representation. Okay, so that phasor that is varying with respect to frequency. Okay, here. So in polar plot, it is the graphical approach. So we are doing basically amplitude and phase with respect to the frequency in a single plot. Now, in case of polar plot, which can be drawn between magnitude and phase with respect to frequency from 0 to infinite, see what's a polar graph sheet? What is a polar graph sheet? Let's observe. Let's have a look on the graph sheet. What we are obtaining over there. This one is the real axis. Okay. This one is the, suppose, imaginary axis. So it is the real axis. It is the imaginary axis. So you may say it is a isomer representation also. Okay. Here this is basically from the origin to any point, suppose any point we are considering. So whatever be the length of the length, that means we are joining that. Basically, this is the representation of the vector. So vector means what? It's having the magnitude, or the phasor is having the magnitude as well as phase. So what is the representation of phase? Very clean and clear about this matter. That is with respect to positive x-axis. What is the angle in between this the straight line? Arrowhead is representing basically the direction. Okay, from 0 to that point, the line segment having the length, that is called the vector length. That is nothing but the magnitude of the vector. Okay, and what is the phasor? Phasor is nothing but the angle of this straight line, direct straight line with respect to the positive x-axis. So that will be termed as a phase. Okay, so vector phasor having the magnitude as well as phase. So how to relate with the magnitude? Magnitude is nothing but the vector length, and what is the phase angle in between the positive x-axis or real axis with respect to that straight line, that will be termed as a phase. Okay, so in case of polar plot, magnitude and phase both simultaneously, that will be observed with respect to omega. What is the variation? Okay, that will be observed. So in this case, what we got, this having the what we can say, the polar graph shift. So here we are obtaining 0 degree, then that will be 90 degree. While we were plotting, we'll be doing the rough sketch also in the plain paper. So what we'll get, we will get that this is our real axis with a 0 degree. That means it is representing the real axis. This negative real axis, and obviously it will be minus 180 degree. Okay, and this will be 90 degree. And this will be plus 180 degree. This will be 90 degree. This will be 270 degree. Now, as it is 270 degree, so what you can say, it will be minus 90. Money that is coming from this basically clockwise. If it is clockwise, then it is obviously the convention of the angle is that if it is clockwise, that will be represented as a negative angle. So if it is clockwise, it is negative angle. If it is anti-clockwise, it will be regarded as a positive angle. That's the angle convention. Okay, so it is minus 90 degree. It is then minus 180 degree. Then it is 90 degree or minus 270 degree. Okay, so that concept should be very clear. Okay, or it will be 360 degree also, you can regard as. So 0 degree, 90 degree, 180 degree plus 270 degree, or if we are coming to anti-clockwise, what we are getting negative angle, minus 90, minus 180, minus 270. So it is same observing over there, only the positive representation is there. So negatively you can think about this is the anti-clockwise direction, you are getting the positive angle. If you are going through the clockwise direction, there will be the representation of negative angle. Okay, so let me do a sketch. And what we have here, convention, the concentric circles or the radial lines representing the magnitude and the phase angle represented. Okay, respectively. And angles are represented by positive values in anti-clockwise direction, that is a positive angle. And similarly, we can represent the angles with negative values in clockwise direction that I have explained. Okay, for example, the angle is 270 degree in anti-clockwise. It is moving like this way, anti-clockwise. So it is the positive angle representation, and same angle will be represented by minus 90 degree. That means it is the negative angle representation. It is clockwise. Okay, that is explained over there. This is written over there. So I have explained it. Okay, so this is all about the polar graph sheet. Now we will move into the next part. How to represent and what are the steps to be followed to get the polar graph. Very simple. Substitute S equals to j omega in open loop transfer function. Because what I told you that open loop transfer function is maybe a system representation or open loop transfer function may be a response representation. Okay, what I am telling you, open loop Wheelchair may be a function, what you can say, the system representation, GS, HS, GS is system representation, or LTF may be representing as a response representation. Response. Okay, that is also GSHS. That's why it is very important. Now, how it is response representation? If RS we are taking as unity, then what is CS? CS is basically response, right? CS is basically, we are talking about the response. CS is basically GS into RS, right? That means what I am talking, RS is the reference input or desired output, and instantaneous output we are getting in the form of CS with the system GS. So what is basically GS? Transfer function of the system, OLTF, and that is CS by RS. So what we are getting, CS equals to RS into GS. Okay, now if we are taking RS as unity, so what will be basically RS as unity? What will be basically CS equals to GS? That means if you are taking LTF, so it will be the system representation or it will be the response representation. Very much important concept to be in mind. Okay, so let's clear my sketch and we are moving forward. So find the starting magnitude, because we want to fit our omega should vary 0 rad per second to all the positive quantities we are considering, all the positive values we are considering, omega rad per second, infinite rad per second. Okay, so with the whole range of positive range of omega, we are considering basically the magnitude and phase of the phasor. Okay, so what is the starting magnitude and phase? Starting magnitude and phase, because it is varying with respect to omega. Okay, we have to fit omega equals to 0. Okay, then we can say that polar plot is starting from omega equals to 0. So obviously starting magnitude will be there and starting phase will be there, phase angle will be there, right? Similarly, finding the ending magnitude as well as phase, we have to fit omega equals to infinite. So as because our range of the frequency and the frequency response analysis now, omega is starting from 0, DC value, to a very high frequency range, that is infinite. But all the positive values of omega we are considering. Okay, all the possible values. So this is basically the getting the phase angle as well as the magnitude for the final value of omega. Okay, now sometimes in between this omega and omega equals to infinite and 0, there may be we need to find for numerical to numerical, it differs. We must have to find certain intermediate values. Okay, so what are the values that may be considered? There's the real axis, polar plot intersect, that may be intersecting real axis as well as the imaginary. Let me just introduce that part. So while we are taking, suppose in phi for omega equals to 0, we are finding that 0 degree, but magnitude is unity. So suppose just rough sketch, there is 0 degree. There is a representation in polar form. Okay, with respect to omega equals to 0, we found for a certain numerical, suppose. Then avoiding all intermediate values, omega is starting from 0 to infinite. Okay, so suppose at infinite we got the most of the time you will get for a strictly proper system, omega for infinite we will get 0 magnitude with the phase angle, suppose 90 degree. Okay, with the phase angle suppose minus 90 degree. So in that case, what we can say is intermediate value starting from 0 degree to minus 90. So all it is covering this, what you can say, this part. Okay, that means the fourth quadrant. So it is starting from 0 degree 1 value magnitude, and it will end to 0 magnitude with the angle minus 90 degree. So what we done in the previous slide, it is the minus 90 degree that is suggesting. So that's why it is just reaching minus 90 degree over there. And what is the magnitude? Here the phasor or vector length will become 0 while it is merging to it is attaining 0 or origin, right? So what is the distance from origin then? 0. So that is the magnitude of phasor. So in this way we can draw. Okay. And what is the intermediate value that may be done if we are selecting any intermediate omega value in between 0 and infinite. That is required. Okay, for this case, what we get, we must have to find out the intersect. It is not intersect with respect to real axis or imaginary, but in certain numericals, you will get this kind of plotting where you will get this kind of plot. Suppose. Okay, so what you are getting, what you are getting here, it is not part. Hmm. Okay, so suppose we are getting this kind of graph. So for this case, vector is moving from this value to 0, but it is covering minus 90 degree cross as well as minus 180 degree cross. That means j omega axis, negative j omega axis it will cross, as well as it will cross for certain numericals, it will cross positive real axis also, and it is meeting at the point that is 270 degree, minus 270 degree, okay, or 90 degree positive. Okay, so if this certain this will be the certain case, in that case you have to find that intermediate frequency where it is meeting minus 90 degree angle or it is intersecting minus omega axis. So you need to find what is the particular frequency where the intersect will occur and the respective magnitude, and you can say the phase you have to find. Similarly, whenever this is cutting, there's a purpose. That's why this is very much needed. Okay, I'm coming. While we will be flow with the polar plot with a much more numerical, then that will be clarified. Again, it is required to find also the negative real axis intercept. So in that case, you have to find that particular frequency where it is intersecting the real axis, and that particular frequency having it the particular magnitude as well as the phase. You need to find it there. Okay. So see, for this specific case, where you have to find that polar plot intersect with the real axis as well as polar plot intercept with the imaginary axis. Okay, so what is a common concept is that if the polar plot having fine, but having its rectangular form a plus jb. Okay, so whenever you have to find the real axis intercept, so what do you have to do? In case of real axis intercept, in case of while the polar plot is moving and it is crossing the real axis, so in case of real axis intercept, you need to find, suppose, this distance, 0 to suppose O, O to A. Okay, so that vector length, how could you find? As this is the concept is that it is attaining minus 180 degree, right? At that particular frequency, it is attaining 180 degree. That means you have to find the particular frequency, and then you are putting the value at particular, putting the magnitude value you need to find at that particular frequency. Then you can get the intercept, because this length is nothing but the magnitude of the vector at that particular frequency. So you can find it is one way. Or other way is that just go straight where you are getting the magnitude a square plus b square, right? But see, how can you find the omega at particular frequency you are getting the magnitude? Okay, where the imaginary part will be 0 at the real axis while it is crossing the real axis, because it is pure, completely real value. Okay, so put the imaginary part jb, that will be equals to 0. And from where you are getting the magnitude where it is completely a real what you can say, a real value. Okay, it is achieving. There is no complex part. Okay, so these are being only the real value. It's a complete real phasor. Okay, so real value phasor. So you are getting only the real part, and then you are putting that particular frequency in this expression. You will get the magnitude also. Okay, there are the two approach. One is, see, here it is written, check whether the polar plot intersect the imaginary axis by real part making 0, or in case of the intercept with the real axis, put imaginary part equals to 0. So vice versa. If it is, if you are putting imaginary particles to 0, so you are getting the real axis intercept because the magnitude will suggest the real axis intercept. Magnitude means the vector length or the phasor length from the origin to that intersecting point, right? And similarly, in case of the imaginary axis intercept file, you need to find where the real part will be equals to 0. So you have to segregate the real part and imaginary part. Or in other way, in the angle concept, you can just have that idea while it is crossing the geometric axis, where what you can say, it is attaining minus 90 degree or plus 90 degree. While it is crossing the real axis, it is attaining minus 180 degree angle. So from that angle concept also you can find the omega and then put the omega in the magnitude part, you are getting the intercept. Okay, I'm coming. That will be clarified later on. Let me clear my sketch and we are moving to the next step. So it is nothing special to say regarding the polar plot. It is like an indicator in the polar form. We are plotting with respect to the variation of omega. What is the range suggest for the polar plot? 0 to infinite. So blindly positive part of the omega. Okay. So blindly we will follow the method and we will find the polar plot. So it is nothing special. But what will be the physical interpretation from the polar plot we want to get, we want to visualize, that will be clarified in our next lecture. That is the stability. So we will be interlinked with the matter of the stability. Whenever polar plot, it is the what you can say method and mechanism through which we are obtaining the polar plot of any system. Then we will find what is the stability of the system. So we will conclude regarding that matter. And how could you get the concept of stability? That will be explained later on. Okay. Now moving with the methods only, we are concentrating how to draw. Okay, how to draw. So this is the example number 1 I set for you. That is for any kind of first order system we are taking here T1 plus ST. So highest order is of the index is index of X is unity. This is of representation of the first order system. So what is this? Gs equals to K divided by 1 plus S star. Now putting S equals to J omega, what we are getting? K divided by 1 plus J omega T. Tau, right? It will be better tau. Tau is the time constant representation. Okay, and this is only a single pole, right? So what is the polar form? Magnitude and phase you have to analyze. So what is the magnitude? Obviously more of that. So what we are getting? K divided by root under 1 plus omega square tau square. And what is the phase? Angle G omega. That will be for the denominator. It has having the angle that is tan inverse of omega tau. So it will be real part. So only having real part. So that's why it is 0 degree. So what is the total angle contributed by G omega? That is obviously 0 minus tan inverse of omega. So it is minus tan inverse of omega. In this way, it is coming minus tan inverse of omega. So what we get? We got the magnitude K divided by root under 1 plus omega square tau square. We got the angle that is minus tan inverse of omega. So for both of these two cases, we are getting the dependencies on omega. That's why we are varying the omega range from 0 to infinite. Now see, for the initial value of omega, while BC, we are considering the BC as omega equals to set 0 because our omega is ranging from 0 to infinite in case of polar plot. All the positive values we are considering. So if omega equals to 0, so what is the magnitude? We are getting K divided by 1 plus 0, right? K divided by root under 1 only. This part is 0. So what we are getting? Value of K. So our just try to realize our vector and the phasor having the starting magnitude K. And what is the starting angle is also important because we have to go to the polar plotting. That means the polar form is very much important. So we are obtaining what is the angle at omega equals to 0. Just put the angle omega, the value of omega that is equals to 0. What we are getting? It is tan inverse of 0. That means it is starting from 0 degree. So if I say you have to represent a polar quantity in phasor quantity in polar form, phasor in polar form, so K is the magnitude. That means the distance from the origin to the tip of the vector or phasor. That is basically the representing the magnitude. And what we found the magnitude K. So it is basically nothing but from the origin to that point A, that is basically the vector magnitude of the phasor magnitude is representing K. Now what is the angle? Angle is 0 degree. So as it is 0 degree, again you have to just go to the just put there plus 90, plus 180, and plus and minus, that should be very concerned. Okay, plus 90, then plus 270, according to the convention of the angle only. Then it will be minus 90 anti-clockwise, minus 180, then, or you can say it is minus 270. Just opposite of plus 270, it is minus 270. Okay, like that way. So it is coming K with the angle 0 degree. That means what is the representation? K is the vector length, and what is the angle? Angle is 0 degree means with respect to positive x-axis. So our vector is now lying along the positive x-axis. That means if it is the positive x-axis or real axis, positive real axis. So what is the angle between the real axis and the vector? That is 0 degree representing over here. Okay, so it is K 0 degree. Now, at omega tends to infinite. So what may be its magnitude? If we put the value at omega equals to infinite, so what you get? It is infinity. K divided by infinity, that means it is becoming 0. So magnitude is 0. And what is the angle? Angle is, if you are putting omega infinite, so you are getting minus 90. Right? Tan inverse of infinite, that is representing, let's say, 90 degree. So minus 90 degree is the final angle. Okay, so at the final frequency we are considering, that is infinite whole range, and where magnitude we found 0 and angle is minus 90. So how to get that T also? Okay, it is minus 90, so it is aligned with the minus 90. And what is the magnitude we found? That is 0. 0 means it is basically emerged into the origin. Okay, so how could you represent? And with the intermediate, if you are just novice, just you can find the intermediate magnitude as well as frequency also. With respect to frequency, that is 1 by tau, 1 by time constant we are considering over there. So k root under 2, because k divided by 1 plus 1. So you are getting k root under 2 plus z omega will be 1 by 1, that's minus 45. Okay, so you are attaining over there at that t, the vector is attaining at omega equals to 1 by tau, is attaining basically that magnitude. Magnitude is 1 by root 2, 45 degree. Okay, so suppose it is 45 degree, minus 45 degree. Then again finally it is reaching 0 with the vector length, and the angle is 90, minus 90. So how could you draw it? So you have to start from here. Just the polar plotting while you are sketching, that is only each and every point for each and every omega we are not finding. We are finding the initial value and the final value. If as when required, we need to find the intermediate 1 or 2 magnitude or phase. Okay, so in that case, we are finding here it is starting from k in 0 degree, so it is end up here minus 90 degree and along with minus 45 degree. So you are just sketching the, what you can say, the rough sketch. Okay, free sketch you are drawing over there. So what you are getting here, k 0 degree, then it is end up to 0 magnitude with the angle minus 90. So it is aligning. See, it is touching minus 90. So with the angle minus 90, it is emerging at the origin, in the origin. Okay, with the origin, it is emerging. So that's why the vector length will become 0. So it is representing over there. So in this way, you can represent the polar form of the, what you can say, this transfer function of the system or the response of the system that we have discussed. Okay. So M5 form you have to represent with respect to the whole range of omega. So you are considering over there initial value of the omega as well as the final value of the omega. Okay, then just put the rough sketch. It is enough. Okay, exact values, exact magnitude you don't have to put here. You just have to put the rough sketch. Okay, that is enough to understand the relevance that we are doing. We will be doing in the next class. Okay. So while creating polar plot, the angles in the anti-clockwise direction that will be considered positive. That is the concept of the angle. Okay, so anti-clockwise angle is always considered as positive and clockwise angle will be considered as negative. And polar plot for previously mentioned transfer function will be given as, I'm coming to that matter. Okay, in the next slide. See here, the direction of polar plot will be starting from omega equals to 0 to omega, it will end to omega towards infinite. Obviously, so that's why it is the directed graph and it is moving from what was the value that was k with the 0 degree. You can write like this way, that will be easier for the understanding. Okay, and k will be 0, magnitude will be 0 with the angle minus 90 degrees. That will be easier to draw also. Okay, so my suggestion is just put here the point as well as the point at omega equals to 0. But here you have to write, you may write magnitude versus magnitude and phase. That is polar form. Here also polar form of that phasor. You can write and then just draw the rough sketch. Okay. So between this point, there may be a few points you can find real or imaginary axis cut that I am moving towards the next part. Okay. So in this way, the polar plotting may be done. So what is the steps to be followed? Is put the transfer function WLTF in the WLTF, just steady state response we are finding the frequency response. That's why AC equals to j omega, and then you get the magnitude as well as the phase, that is polar form of that GS. Okay, G j omega you can say, and then just put omega equals to 0 and infinite. You are getting the initial magnitude as well as phase polar form, and put in polar form k 0 degree over there, and final value also magnitude as well as phase, and then just put the rough sketch. So you can draw like this way. It is not essential that you are putting just circular or something else. So you can put a rough sketch. Okay. So let me clear. And then, so what is the steps? Okay, to get to the intercept. Why intercept is needed for the special purpose and coming. Okay, so general rule is for the polar plot to cut the real axis cut. Real axis cut means that is cutting the real axis like this way. Suppose. So for the real axis cut, you have to find OA that vector length. Okay. So obviously that particular frequency you need to find. What is the frequency that it is basically attaining minus 180 degree you can find, as well as the frequency you need to find. That means most want matter over there is that you need to find the particular frequency. Okay, so how to do it? So in that case, for the polar plot to cut the real axis with imaginary particles to 0. G j omega having its real part and imaginary part, you are segregating G j omega into two parts. One is the real part as well as the j omega part. Okay. J omega, that means j imaginary part. Okay. I j part. So the put the imaginary part that will be equals to 0. So you are getting a particular frequency, right? You are getting the particular frequency. Obviously, that will be in between 0 to infinite because your whole range is starting from 0 to infinite. Okay, then you can get the particular frequency only. So you are finding the particular frequency where it is meeting the real axis. Now, how to get the intercept? How to get the intercept? You have to get the intercept from the magnitude, because see, intercept means that length from the origin. So how to get? Put that particular frequency at omega. At omega equals to, suppose this is omega 1, where it is we have obtained from this imaginary part to be equals to 0, we are getting omega 1, that particular value. And then at omega 1, what is the magnitude we need to find? And that will be obviously representing here the magnitude of it. It's very simple. Okay. And in case of polar plot, okay, this is the first method. Now for the second method, you can find that in this way also. Your phasor is getting, G omega is getting the angle minus 180 degree, right? Just put G omega angle that is equals to minus 180. So you can find in this way omega 1. Okay, so other way to find the omega 1 at which it is attaining, the phasor attaining real axis, negative real axis. So find omega 1. Then from where you put the magnitude at omega, you find the magnitude at omega 1, that will be the intercept. Same procedure, but same result, but you will get the two procedure. One is you have to segregate the real axis and real part and imaginary part. Put imaginary part equals to 0. Find the corresponding frequency. Put the corresponding frequency in magnitude. You are getting the intercept. Similarly, if you are going to the angle approach, so put g omega angle that is equals to -180. You are getting the corresponding frequency and find the magnitude at that particular frequency. You are getting the intercept. Okay. Now, second one is while you are finding the part with respect to imaginary axis. So part with respect to imaginary axis means negative. Suppose if it is, it will be attaining -90 degree. So it is the angle method. So you need to find that particular frequency, omega 2 suppose, and magnitude at omega 2. So you will get basically the intercept with the imaginary axis. Or even if it is 270 degree or plus 90 degree, so you will get that intercept also. So you need to find basically that particular frequency where it is attaining that particular angle. Okay, this is the angle approach. And what was the first approach? You need to find the imaginary axis intercept. So at that imaginary point on the geometry axis, real axis part will become 0 because it is purely imaginary. Phasor then will be purely imaginary, having the purely imaginary part. So put the real part equals to 0. You will get the particular frequency omega 2. Then again at magnitude at omega 2, what you are getting the magnitude, that will be the imaginary axis intercept. Okay, this is a concept. So we will be following. Next is we are taking the example. So another example to get the concept. Okay, much more better. So what is GS? We are representing here the second order system. It is representing the highest order of S in the denominator polynomial. Can you remind? So K divided by 1 plus S star 1 plus 1 plus into 1 plus S star. Okay. So again same approach. You have to find S equals to j omega. Then you have to find the magnitude. So what you are getting for different phasor, it is very simple. Don't arrange that phasor. Just put the phasor only. You have to put S equals to j omega. Okay. So if you are putting S equals to j omega, you are getting these two phasor, and separately you are considering the magnitude. That will be easier. Okay. So root under 1 plus omega square tau square, and this will be also for that same purpose. Now what is g omega angle? Minus tan inverse omega tau 1 for the first part, and this is minus tan inverse of omega tau 2 for the second part. So as a whole, you are getting the summation of these two. Okay. And now for omega equals to 0, what is angle g omega? You need to find as well as phase magnitude, right? That is the starting polar in 5 form. Okay. So what you are getting here? K 0 degree as same as the previous numericals. So it is for the starting phasor magnitude value as well as angle with respect to aligned with the positive real axis. And what is the magnitude? K. Now for the omega tends to infinite. What is g omega? That will be equals to 0 and angle g omega will be -1. Okay. So what you are getting here? That is the magnitude and the phase is -180 degree. So these are two information we got to derive from the polar form of the system. Okay. Now just keep it in mind. K0 degree is the starting, and finally it will emerge to just try to interpret. Okay, it is starting with the vector length K and it is ending with the vector length 0. That means it is again emerging to the origin, right? And with the angle 0 degree it is starting, with the angle -180 we are starting, and it is ended. Okay, so that's why it will be easier to realize. Now let me clear my sketch and we are moving forward. Okay, so I'm coming to that matter. So before going to that matter, let's see what is the sketch I have presented over there. That is K 0 degree. There's a polar having magnitude polar form, magnitude and phase, and it is ended to 0 magnitude with the phase angle -180. So just put there. So what we did? K0 degree, it is starting and it is obviously crossing minus j omega axis, negative real axis, imaginary axis, and then it is emerging to the origin, right? Vector length becoming 0 and with the angle -180. Very simple. Okay. So it's freehand sketch. So you are sketching this one. Now moving to the analysis part, where you have to find out the intercept that vector length while it is attaining minus 90 degree. The phasor is attaining minus 90 degree. Or phasor is crossing minus j omega axis. That means real part will be equals to 0. So I'm coming to that matter. Okay. So what is the second steps you need to follow? Whenever the phasor is crossing the j omega axis, there is the intercept with the j omega axis. So you need to find the intercept. Okay. So let's move to the previous slide. So what we get here, it is basically, see, this is a vector representation with the j omega is equal to j omega. So we are segregating over here the real part and the imaginary part. How to segregate? It's very simple. Just opposite phasor you are multiplying. That is the concept, okay, of the algebra, you can say. So where you are getting this one is the real part, this one is the imaginary part. So if you need to find the imaginary axis purpose the graph, polar plot. So you need to find the imaginary axis intercept, so real part becomes 0. So what is the real part? We are finding this thing. So obviously it is a numerator part. So numerator part, taking numerator part as a 0, we are getting omega. What is the particular frequency where it is crossing the j omega axis? That is omega equals to 1 by root under tau 1 tau 2. Right? So we are getting that concept. We are getting that value from the, of the omega. Right? We need to get now what is the magnitude at omega, right? What is the magnitude at that particular omega we need to find. And that is nothing but the intercept. That is nothing but the intercept with the of the minus j omega axis. Okay. So what you need to put now, putting this real part value of j omega that we are getting here 0 and putting imaginary part to be 0, obviously it will be resulting 0, hence the polar plot does not cut the real axis. We don't need to find it because we have the rough sketch where we are getting, there is no concept of the real axis cross section. So that's why we have to avoid that part. We will only proceed with the geometric axis intercept. So we got the value of the omega where it is crossing the geometric axis. Now we need to find only the vector length. So we are finding here the phasor length from the magnitude. So we are putting the magnitude part where the putting the magnitude part, and what we are getting k root under tau 1 tau 2 divided by tau 1 plus tau 2. So only this part is our concern now. So this part, sorry, magnitude part will be 0. Sorry, this part is not concerned because it is already 0 while it is crossing the j omega axis. So what is the magnitude we are getting from here? Okay, so just put that value and we are getting the magnitude. Okay, so in this way, or another approach is that what was the angle? Let's find what was the angle. Okay, what is the angle? Minus tan inverse of omega tau 1 minus tan inverse of omega tau 2. So here it's very simple. Okay, minus tan inverse of omega tau 1 minus tan inverse of omega tau 2. That will become minus 90 while it is crossing the j omega axis, right? So minus, taking common, minus minus cancel. So we are getting tan inverse of omega tau 1 plus omega tau 2 divided by 1 minus omega tau 1 into omega tau 2, right? As a concept of the tan inverse of A plus tan inverse of B. So we are getting here 90 degree, okay? So as it is 90 degrees, so what is our concern? Our concern is total angle will be infinite. The value will be infinite, right? So omega tau 1 plus omega tau 2 divided by 1 minus omega tau 1 omega tau 2, where we can say if it is becoming infinite, then we will get 90 degrees, right? So if that part having infinite value, that means what? Lower part, denominator part is equals to 0. So we are putting here 1 minus omega tau 1 omega tau 2, that means omega square tau 1 tau 2, that will become 0. So we are getting, what is the omega value that we found in the previous slide? The same value we obtained. Now what is the magnitude of that phasor? We got that concept, that is if we put tau 1 tau 2. So what is the magnitude? Let's Okay, so we are getting the magnitude at particular omega, that is 1 by tau 1 tau 2 into root under tau 1 tau 2 we found. So here it is crossing the geometric axis. Okay, so what is the magnitude part? That we are putting omega equals to 1 by root under tau 1 tau 2. Okay, 1 by root under tau 1 tau 2. So k divided by root under 1 plus 1 by tau 1 tau 2 means it will become tau 1 square divided by tau 1 tau 2, and here it is 1 plus tau 2 square divided by tau 1 tau 2, right? So what we are getting here, k divided by tau 1, 1 tau 1 cancel, 1 plus, or rather say tau 1 plus tau 2 divided by tau 2 root under, and here is also multiplying with tau 2 1 cancel, so we are getting tau 1 tau 2 again by root under by tau 1 whole root under. So ultimately what we get? Ultimately we will get k divided by, okay, root under tau 1 tau 2, that will be the numerator part, so tau 1 tau 2, and uh, root under tau 1 tau 2 into root under tau 1 tau 2, so it is becoming tau 1 plus tau. So this is the magnitude of the phasor at that particular frequency omega equals to 1 by root under tau 1 tau 2. Okay, so this is the intercept where it is meeting the geometric axis. Okay, and what is the magnitude we found? The magnitude we found, this is the magnitude. So you need to mention over there at omega equals to 1 by root under tau 1 tau 2. What is the magnitude we found? That is the magnitude. K root under tau 1 tau 2 by tau 1 plus tau. Okay, so let me clear my sketch and we will move forward. So what we get the concept here. Now, what is the main objective? We found any phasor we will be given, we can draw the polar plot. Now, what is the physical interpretation? What is the utility of this polar plot in the context of the control system? That is very important. Okay, so it will be utilizing for the stability response, stability analysis. Okay, so while I am coming coming to that concept of just blindly you have to take on me and just put here whenever it is crossing, whenever it is basically crossing the real axis. Okay, so if it is not including minus 1 j0, that means what is minus 1 j0? Suppose it is minus 1 j0, that is the point on the S-plane, S-domain. Okay, S-plane. So while our suppose polar plot we are getting like this way. Okay, so this for cross-secting the real axis, negative real axis at that point. If it includes minus 1 point, if the vector length is greater than 1, then it will include minus 1. Okay, then it will be terming as a unstable system. If it is just not including minus 1, only like this way, that polar plot will be given. It is not including minus 1 j0, so it will be terming as a stable system. Okay, and I will be interpreting the same issue later on, not today. So what we have here, see, so you have here minus 1. Why that minus 1 point is very much important? As because our consideration is that we are handling basically the open loop transformation. We are not handling basically the characteristic equation. So that's why TS is taken as 1 plus GSHS, right? So if GSHS having the center at origin, sorry, 1 plus GSHS having the center of origin, GSHS having the center of origin, right? And now origin will be shifted to minus 1 0 if we are considering it is 1 plus GSHS as a phasor, right? So if the phasor is GSHS, our origin will be considered as 0 0. we are dealing with GSHS always, because 1 plus GSHS is additional headache for the calculation. So what is simply intelligent matrix, that here GSHS, let's consider analysis will be, plotting will be done through GSHS, but we will be analyzing the characteristic situation of the system, of the closed system, right? So 1 plus GSHS is the characteristics expression, and what will be the origin taken into consideration in that case? It will be shifted to -1, right? So our approach is, we will be handling open loop transfer functions GSHS, but we will be analyzing 1 plus GSHS. So that is the characteristic equation of the system. Very much important. So then we can analyze the system as a whole, right? So in that case, if it is including -1, so it will be unstable. If it is excluding -1, it will be stable. Okay, like this. So the stability, that part that will be discussed in the Nike stability criteria. Okay, that will be discussed. Just you have, you just to find out what is the intercept with respect to the real axis. It is very important, because that will be basically connected to the in the Nyquist plot, that will be connected to the stability of the system. Okay, so that's why if -1, 0 is the left of the polar plot, it's not enclosed, then the system is stable. If the -1, 0 point, J0, better to say J0, okay, that is included, then it will be unstable system. And if -1, J0, just over that point the phasor is passing, then it will be turning as a marginally stable system. And that will be interpreted in the Nyquist lecture. Okay, so for today enough. We have got the concept of how we phasor that can be plotted in the polar plotting, and what will be the physical interpretation with the stability, that will be discussed in the next chapter. Only the method you have to follow blindly, and you have to find the intercept with the real axis. So sometimes you need to find the geometry axis intercept, but it is not so important. Only with the real axis part intercept, it is very important because it is directly connected to the stability analysis. Okay, so